Oh, welcome. Let's continue from where we stop. I want to start from section 1.5. Allow me to share my screen and then we continue from there. Section 1.5 is on unit of measurement. I like to have my whiteboard. Let me just have a setting right here so that at least you can see my notes. In chemistry, a measurement is, or a measurement consists of two things. This is number, all right, plus a unit attached to it. Otherwise, if we say the distance from Jacksonville to Miami is 358 without indicating the units, 358 will just be a meaningless number. So all measurements should have two things: a number attached to it and a unit which goes with it. This is the unit, and this is a number which shows the magnitude. There are three types or three systems of measurements you should learn, be familiar with. This is the metric, all right, the metric system, which we use in school. In the lab, we use metric system for most part. And then there is the system international, or we call that this is just SI, or stand for system international, system international, founded in 1960 by a group of scientists. And lastly, this is the English, which we use at home, or mostly we use in the US English system. Whatever you pull by the car station, the pump dispense gasoline in gallons, all right? When you drive on highway, freeways, or even in the neighborhood, the speeds are posted, they are posted in miles per hour, miles. That's an English system of measurement. Yards, for example, that is system of measurement, just to give you few examples of English unit of measurement. So these are the three systems. So when you see here, SI unit stand for system international, okay? There are seven units, seven base units you'll see, all right, used in the SI unit. You should know the base unit in System International in comparison to the metric. For example, here, let's say the metric and SI. If I have mass, all right, mass, measuring mass, we use here gram, here is kg, kg, kilogram. For volume, all right, volume liter, this is meter cubic, all right. You see on the screen mass, kilogram for SI unit. The temperature for T, Degrees Celsius, Kelvin. We will see later on the unit of O3 system for expressing temperature. All right, just to give you a few parallel examples between the metric and the what and the SI system international. Amount of substance 1 mole. I know you'll see this. Chemists use this, which is the piece unit of measurement in SI, which represent Avogadro's number of things. You'll see this down the line. 2, 3 things. Anything you can think of. If you have 1 more talking about the this number of items, Avogadro number. We'll more look in details later. All right. In US, is the metric is gaining traction in terms of usage. Most of the measurement are indicated in both English and the metric, English and the metric system. What you see here, ML reducing the base unit, we'll see later on the prefixes used to reduce or increase the base unit in metric. So here, base unit in metric system, ml milliliters, reducing the base unit of liter per 1,000. So for metric system, we use grams for mass, length for meter, and second for time. So remember that. Don't get confused with the kilogram for what? For the SI unit. SI unit. Temperature degrees Celsius, these are highlighted base unit in metric system. Amount of substance I've indicated here on my whiteboard, the numerical value, which represent the what we call mole in measurement. So we have that Avogadro number. So I'll see that cubic milliliters. These are the prefixes used in increasing or reducing the base unit in metric system. All right, reducing or increasing. Please, you need to know the prefix when we say peta, abbreviated PS in Pole, it means you are increasing the base unit by 1 times 10 to positive 15. It can be petameter, all right? It's different from picometer. Picometer we'll see later on, the italic for that. You have seen terabytes. A byte is a base unit of storing information in computers. And when we say terabyte, you are increasing it by 1 to positive 12. Gigabytes, megabytes, which is different from the million. Micro, we use the Greek symbol, all right? What I want you to take on from this slide is knowing the names, all right? You need to learn the names as well as the abbreviation and have the meaning, the numerical value by which either the base unit is increased or decreased. For example, microgram, all right? Microgram means you have reduced base unit in metric system by 10 to negative 6. Milligram, for example, mg, all right? This stands for milligram. Microseconds, all right? Milliseconds. Deciliters, that means times 10 to negative 1. Decimeters, all right? Decimeters, there is the centimeters, you know, the centimeters, centiliters, and so forth. Those are the abbreviation used in increasing the metric system. Now, we don't have, or we don't use these abbreviation, the prefixes in English, all right? And SI, this is only for metric. This is only for metric. Please learn those, you may see in the quiz. Nano, reducing the base unit by 10 to -9, pico to -12, femto, and so forth. Please learn those prefixes. This is just a learning check to see if you, or what kind of question you expect in the exam or a quiz. What exponential notation, all right, do the following abbreviation? DAISY, all right? We're gonna have that DAISY, D for DAISY, and we will have that, that means 1 times 10 to -1. A, all right, A is 1 times 10 to -1, DAISY. And then M for mega, all right, this is 1 times 10 to 6, could be megagram. And then pico for 10. Remember, this is the lowercase p, it's not the uppercase p. Let's go back to where we are. If you look at this, right, this is a lowercase p. How about this one, uppercase p for peta? Please take note of that, so that this is, C here is 1 times 10 to -12 for pico, all right? For pico. So you can be asked a name, all right? This is DAISY, this is mega, and this is pico, all right? Pico. This also asks you, the follow-up question here is to see if you can translate to the symbol, the appropriate metric prefixes used to write the following measurement without using the exponent. You see, this time is 10 to -6. So what I'll have for this is 4.7, all right, microgram, right, times 10 to -6 is micro. So it's coming from here. You see this right here, times 10 to -6. We don't have times 10 to -5. Somebody asked me before, but this is what you only need to learn. This is what you only need to learn, right? This is A, and B, 1, that will be 1.85 times, not times, but we want to use the symbol, the prefix. This is picowatt. This is pico meter, instead of 1 times 1.85 times 10 to -12. So this is what I'm looking for. And this one, if the question is along these lines. All right, let's look at the mass and length measurement in metric mass here. Is simply used to define the amount of matter in an object, all right? It's simply the amount of matter in an object, and mass is a measure of amount of material, amount. Okay, SI unit is the metric which I gave you earlier on here, that in SI we use kilogram, in metric we use gram. Please take note of that, so that you know the SI versus the metric. Length is a measure of distance, and the base unit in metric we use meter. Volume, this is just how volume was arrived. We use liter in metric, just reducing that by 1,000 milliliters. One equivalent statement, you will find it useful down the line, is 1 ml is the same as 1 centimeter cubic or cubic centimeter. If a cubic is 1 pi 1. It's the same as 1 ml. I don't want to spend time on you know, this comparison, but just in lab, these are just few class where you will see or you may have used before in measuring volume of liquid substance. This is graduated cylinder. This is a syringe, puree, right, with stopcock. This is volumetric pipette with the bulb. We call this, you can easily use the pump with the wheel on the side. And then volumetric flask. This is more precise, right? You will use this in preparing solution. And there is a calibration mark along the neck, which include the capacity or indicate the capacity of volumetric flask. The two here, the last two, they are more precise, this one and this one, more precise in terms of the exact volume you want to measure, let's shift gears to temperature, which temperature is simply defined as the average kinetic force or average kinetic energy or motion of particle in an object. All right, so when we talk about the temperature we are referring to average kinetic energy of particles in a substance. There are three units of measurement measuring temperature. There is the Kelvin, there is the degrees Celsius, and degrees Fahrenheit. Degrees Celsius and degrees Fahrenheit, which I want you to learn. All right, the measurement of temperature in three scales: Kelvin, Celsius, and Fahrenheit. This is just indicating the boiling point of H2O at normal atmospheric pressure and freezing point. There will be conversion of temperature from one scale to another, and I want you to know, I know some of you know, changing from degrees Celsius to Kelvin. That means you want Kelvin, it's gonna be given what? Given degrees Celsius plus 73.15 to 73.15. This is easy as that, and you have yourself what? You have yourself temperature in Kelvin. When you see here, this is what is given in the problem, plus 273, converting the given degrees Celsius to Kelvin. So here is given. This is what you'll be given to convert to what? To Kelvin. And of course, you know, given Kelvin, you can say here, Kelvin to degrees Celsius. That means degrees Celsius is given by Kelvin, is what will be given, minus 273.15. You should be able to rearrange the equation. So this one will be what? This will be given. You'll be given in the problem and are asked to change from Kelvin to degrees Celsius. I'm just rearranging this equation. Now, Fahrenheit, right, changing degrees Celsius to here, changing degrees Celsius to Fahrenheit, degrees Fahrenheit. Degrees Fahrenheit is given by, I like 1.8 times degrees Celsius. This is what you will be given. Do this fast, and then you add 32. I know there are other uses, 5/9 or 9/5, doesn't really matter, it's the same thing. And if I want degrees Fahrenheit to degrees Celsius, all right, That means degrees Celsius is given by Fahrenheit minus 32 to that fast over 1.8. All right, over 1.8. These are the equations you change. So this one you will be given. This is the same as what I do have here, 9 over 5. 9 over 5 is 1.8 times degrees Celsius, and then you add 32. You are looking for or converting degrees Celsius to Fahrenheit, degrees Celsius to Fahrenheit. When I look at degrees Celsius, this is the last equation here, is changing degrees Fahrenheit to degrees Celsius. So your question is degrees Celsius is given by degrees Fahrenheit, which will be given. So here, this one is given as part of the problem, and you plug it in the equation, you have yourself the answer. Let's look at the example here. Our weather forecast predicts the temperature will be 31 degrees Celsius. What is the temperature in Kelvin? So Kelvin, if this is what is given in the problem, you're just gonna have plug it in the equation 5, which is 31 plus 273.15. If I look at the uncertainty, we'll look at later on. This is 304.15. This has no place of decimal. This has 2 places of decimal. So our answer will have no place of decimal. We will see later on when we get to significant figures and include the units. This will be Kelvin. We will come back again to why I don't have what places of decimal, because 31 has no place of decimal. It's not about 2 significant figures, but places of decimal determine how to our final answer will look like. And please don't forget the what? Don't forget the units. So with our temperature in degrees Celsius, degrees Fahrenheit is given by 1.8 times degrees Celsius, right, plus what? Plus 32. This is 1.8 times 31 plus 32. This is 87, all right, 87.8 degrees Fahrenheit, 28 degrees Fahrenheit. If I look at what we were given earlier on, this has 2 significant figures, 88 degrees Fahrenheit, 88 degrees Fahrenheit. So sometimes you check, you may have realized that when you check out the answers at the back of the text, is slightly different from what you see on your screen. Please pay attention to significant figures. Pay attention to significant figures. Let's see. There is an important property of matter we call density. It is the concentration of matter. Density is just defined as density is equals to, this is concentration of matter, concentration of matter. All right. So it's a property used to describe matter. Each substance has a unique density. For solids and liquids, all right, it's given in grams per ml or grams per cubic centimeter. However, for gases, all right, it's given mostly in grams per liter in grams per liter. How you determine this density, of course, is given by this. You need to know, all right, where D is what? D stands for density. M, this is mass, and V, this is volume. This is volume. The equation given there, you may derive more than one, but I've seen students using this diagram. I don't know if it's going to work for you. Let's say that, and then I'm gonna put a T here. All right, and here I have mass and what? And here is density and here is volume. I can put multiplication here so that if I'm looking for density, all right, if I'm looking for density, I'll just have to multiply by what? Multiply mass over volume. This means, all right, this means the density, all right, density times, or rather, if I'm looking for mass, all right, mass equals to density times volume, equation 2, or volume equals to mass over density. You should be able to rearrange the main equation, which is this one, all right? Let me call this equation 1. You should be able to rearrange equation 1. Look here, if I'm looking for this, and then it's gonna be this over that, all right? This over that right there. All right, if I'm looking for that mass over volume, all right, mass over volume. Density is mass over volume. Mass is density times volume. There are three areas. And please pay attention to the units, okay? Because you may be given the density in grams per ml, or rather density in grams per ml, but the mass is in kilogram, all right? You need to reconcile the units so that you plug in the equation to get the correct answer. Here is just few substances with their literature value for their densities. All right, let me see if I have ice here. This is density of water. I believe density for ice is slightly ice, all right, ice 0.999, but for H2O, even though it's the same thing, 1.00, this is just literature values, all right? This explains why when you place ice cube on water, it tends to float, because we know less dense objects tend to float on a more dense object. So you see here, water is 1.00 grams per ml or grams per cubic centimeter. It's the same thing. It's the same thing. Let's see. Learning check. The density of benzene at 15 degrees Celsius is 0.8787 grams per ml. Calculate the mass of 0.500 liters of benzene. This is a critical thinking question in the sense that even though you are given the volume, look at the units for density, look at the units for volume. That means you need to understand 1 liter equals to 1,000 ml. So if I convert 0.1500 liters, I'm just using dimensional analysis, which we'll talk about in a moment. So if I have what here is 1 liter, 1,000 ml, okay? This will cancel, that will cancel, and we have 150 ml. This is now what we need to use in our calculation. When I use 150 and mass, all right, we know mass is given by volume times density, which means 150 ml times density, which is 0.8787 grams per ml. This will be what? 131.8. Please check on your calculator. You have that. That is the mass of that amount of benzene at 15 degrees Celsius. I'm using 4 significant figures here. You may have more than one, more than 4 significant, because if you look here, 1, 2, 0 do not count. So we start 1, 2, 3, 4, and here we have 1, 2, 3, 4. So 4 significant figures. I know you may have had this, you may see this in your calculator, 1.1.805 grams. Please, this is not, let's get into the habit of expressing our final answer with the correct number of significant figures, because when you get to the homework, you'll have to pay attention to significant figures, So that's a learning check on how to determine the density of a substance, Now, throughout the course, you'll be handling numbers, you will be multiplying numbers, you will be dividing numbers, all right? And it does not mean that all the digits you see on the calculator will be accurate or correct, okay? You'll encounter numbers, and we'll have to learn how to express our final answer with the correct number of significant figures. But before we get that, there are 2 types of numbers you will deal with, you will handle. There are those numbers obtained from counting. Those numbers are referred to as exact numbers, all right? And even the definition, you see, when we say 12, 12x, well, doesn't, we have to count. We don't need any machine to measure 12, right? 7 days in a week, we have to count. Definition, what do I mean by definition? This is a definition and it is exact, all right? 1,000 ml or 1 kg equals to 1,000 gram, all right? And even these, some conversion factors, 1 inch equals to 2.54 centimeters. Those are definition. It is well given, all right? 7 days in a week, okay, those are definition, they are well defined. And when we get to those, we'll have to differentiate from those numbers obtained from using an instrument to obtain. For example, your height, we may use a metric ruler, okay? Your weight or mass, we may use a scale, all right? Those numbers obtained from measurement, from using an instrument, are said to be inexact. There are some errors associated with it. Having said that, we will look at in detail in section 1.6, uncertainty in measurement. All measurement have, all right, degree of uncertainty. For example, 98.2 degrees Celsius, just to give you a temperature reading, we call this number here exact. We are sure, not exact, but certain, all right? All right, here we call it certain what? Digits, uncertain. Yeah, uncertain digit. All measurement have or consist of certain and uncertain digit, depending on what? Depending on which instrument is used. Always the last digit has some uncertainty associated with it. So remember, no measurement is what? Is exact. Or in other words, there is no instrument which will give you exact number. All right. Is no instrument will give you exact number. Here is just illustration on temperature measurement, somewhere between 20 and 27. We'll be just approximating between what we are sure of is 20 and 30, but anything in between here, there's some degree of uncertainty. There's some degree of uncertainty. Now, there are two terms which you will see, you need to memorize, you need to learn. They are usually used whenever measurement are handled. This is accuracy and precision. I would say accuracy is just telling the truth one time, and precision is telling the truth over and over. You can use your own words so long as you understand. So precision is a measure of how closely individual measurements are in agreement with one another, how close they are, a series of measurements, how close they are is a measure of precision, a measure of precision. But if you are looking at individual measurement, all right, it refers to how close an individual measurement to the true value. There's a diagram in the text. Somebody was playing that. If you look here, these are good precision and all right, good precision. Let me just blow this up. You see, this is good precision and good accuracy. What that means is for good precision, they are close to one another, the arrows, right? For individual, whenever we're talking about accuracy, each one of them is at the bull's eye, all right? Look at one, it's at the bull's eye. That's the target. Even though here we have good precision, right? They are close to one another, but poor accuracy. To be accurate, gotta be here. And this one is poor accuracy and poor precision. They are far apart. They are not close to any one of those. So please read, I think they start example in the text or yes, in the text on precision and accuracy. Those are the key terms I expect you to learn, to memorize. You may be required to define in an exam, all right, or differentiate the two. Let's see, I talk about significant figures. Significant figures are important digits used in expressing numbers, all right? And in this section, you will be given numbers and asked to express the number of significant digits in this number, all right? Or when you multiply numbers, when you divide numbers, your calculator will give you more than what you need. In this section, we'll see how to proceed with calculation and significant figures. But before that, let's look at the rules for counting significant figures. First, you start counting from left, going what? Right. Count from left, going right. And all digits, including uncertain one, are significant digits. Just give you a heads up. All digits, including uncertain one, do count as significant digit. There is rounding off, which you already learned in math class. Of course, you may drop the non-significant digit. If it is greater than 5, the preceding digit is increased by 1, and then you drop the non-significant digit. We may see that when we do the calculation. Let's see the rules. All non-zero digits count as significant. For example, here, 1, 28 crowns. This has 3. If you look at, we start from here, 1, 2, 3. So 1, 2, 3. This has 3 significant digits. I'm just using the parentheses to indicate the number of significant figures or significant digits. So all non-zero digits count as significant. Now, zeros in between non-zero digits count. Sometimes we call here too, we call captive. Sometimes we refer to as captive zeros. Zeros in between non-zero digits. They are captured in between basically. So if I have this 10089 crowns, if you count here, this is what we are talking about: 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, and this one has 5 significant digits. A lot of students face challenges when handling zero. Sometimes zero count, sometimes zero do not count as significant digit. But right now, captive zeros or zeros in between non-zero digits do count as significant. That's why I have 5 there. They are captive zeros. Zeros at the beginning of a number are never significant. Here we call this, let me just rename this, we call leading zeros, and they do not, all right? They do not count, they are just placeholders. A number such as 0.018 centimeters, for example, just give you a measurement. The zeros here are leading zeros. They do not count. We start counting from here, and we say 1, 2, 1, 2. So this has 2 significant digits, 2 significant digits. The zeros at the beginning do not count. I'm just crossing that so that I can figure my brain not to count the zeros. We call these leading zeros right here. These are leading zeros. Be careful when we have a number such as 0.0, all right, 1, 0, 8, all right, 0, for example. I can have a 0 there. Here, the zeros here do not count, right? It will take practice to know. So this one, 1, 2, 3, 4. So 1, 2, 3, 4. This one has 4 significant digits. 4 significant digits. 0 after non-zero. When there is a place decimal, do count. Now, those are leading zeros. And then zeros at the end of a number are significant if it contains an implied place of decimal. These zeros here, some others called trailing what? Trailing zeros, trailing zeros. They do not count unless there is what? There is an implied place of decimal. 2, 5, 0, 0, 0. This has 2. This has 2 significant. But if I have a number such as 2, 5, 0, 0, 0, and then there is an implied place of decimal there, and then this will be what? Look at these zeros at the end of a number are significant if it contains a decimal. This second number has a place of decimal, and this has 5. All right, 5 significant digits. This ambiguity can be taken care of by using scientific notation. All right, it's very easy to count the number of significant digits. Anything on this side of the multiplication sign, regardless of the exponent. All right. If you look at the exponent right here, exponential 4, 4, 4, but anything on the left side of the multiplication sign do count as significant digit. If you look at this, 1, 2, 3, 3 significance, 1, 2, 3, 4, 4 significance, 1, 2, 3, 4, 5, 5 significant. Anything on the left side of the multiplication sign for a number expressed in scientific notation do count as significant figures. Let's see. All right, indicating the number of significant digits. Indicating the number of significant digits. When we say how many significant digits are in this number, all right, the first one has zeros after the place of decimal, and A, all right, A has 4 significant digits. So A is 4 fig. A is, all right, four significant digits. Of B, all right, this has 5 significant what? 5 significant digits or significant figures, because you're counting from here 1, 2, 3, 4, 5. All right. Here, these are captive. This is a captive 0, captive 0, 0 after non-zero digits. This is a place of decimal. Do count. So here is 1, 2, 3, 4, 5, 6. So see, this has 6 significant figures. 6 significant figures. So this is just given what? Given a number and you are asked to state the number of significant digits. You have to practice. This is math and you cannot read math. You have to practice, do more problems in the text on how to count the number of significant digits. Just given the number and you are asked what? To state. Easy. Those are easy questions in the exam, all right? I want to now move on to significant digits and calculation, all right? Significant digits and calculation. And I will group two. There are 2 types of calculation we will encounter. This is addition and subtraction. And then there is multiplication and what? And division. All right, those are the 2 broad categories of calculation. Here in calculation, Magyaro knows what you will be looking here is, look at the list. I will say least number of decimal places. This is decimal places, all right? Maybe I should write it in full. All right, for decimal what? Decimal places. Example is if I'm adding 10.1 plus 2.89, no, 32, for example, your calculator will give you 12.932, okay? This one has, if you look at this has 1 decimal place, and this one has 3 decimal places. What the rule state is the least places of decimal in your calculation will determine how many places of decimal you have. I'm gonna stop right here. And if I look at this, it's less than what? Less than 5. So we just have 12.9, one place of decimal because of what? Because of one place of decimal in one of the numbers. If there are 2 or 3, in this case, if this one had 2 and this one has 3, and then we'll have 2 places of decimal in our final answer. If it doesn't have, let's say 10 plus 2.8 to 3, this is 12.8, all right, to 3. This has 0, all right, this has 3. So that means our final answer will have no place of decimal. This is greater than 5, so we increase the preceding and make it 13. We make it 13 days, round off. Remember to round what? Round off, increase the preceding by 1, okay? We were supposed to stop here. Look at this. This is greater than 5. We round off to 13. So I'll do the same thing for what? I'll do the same thing for our subtraction. This goes hand in hand. Now, multiplication and division, just the way we look at the density, we divide the numbers. Here, you look at the least decimal, least 6 figures. You have to look at the numbers, the number of significant figures. For example, here, okay, you have an example here, 1.2 times 2.33. This one, you'll see, let's say centimeters, with my calculator, all right? 1.2 times 2.33, you see it is 2.796 centimeters square. It's more than what we need in the world of significant figures. We need to round off what? To the correct number of significant figures. And since this is addition, and I mean multiplication and division, this has, all right, this has 2, all right, this has 2, this has 3. Our final answer should have 2 significant starting from here, 1, 2. This right here is greater than what? 5. So we increase the preceding and make this 2.8, and please include the units, centimeter square, not cubic, centimeter square. All right, centimeter square. That's what you need to look at. If you look at what I have, the parallel in terms of calculations, I'll handle the same way, addition, subtraction, look at the places of decimal. For multiplication and division, list significant figures, If there is a mixture of operation, all right, of course, you have to go with the order board, mass that you do bracket. This is stand for bracket. If you have something bracket in parentheses, you'll do that first. And then there is off. This is stand for off. And of course, you know, division, you're gonna do that multiplication. And this is addition. And this is subtraction. All right, I'll follow that sequence, this pattern, when you have a mixture. All right, so here I just went through in brief how to proceed with the calculation. All right, if you look at here, addition, subtraction is performed, answers are rounded to the least significant digit. If you have no significant digit, then you know you just have to round it off. to no place of decimal. Wherever you are looking at multiplication here, you look at the least or fewer number of significant digits. I've highlighted that. You go practice until you master these two rules. I've seen students in the exam, they swap the rules. They use the rule for multiplication, division, in addition, subtraction, and vice versa. Be careful with that, all right? Be careful with the rules. Note the numbers appropriate throughout. Always don't round in between, but carry out the calculation and round off at the end only, not in the intermediate, okay? Always round off the, you have to round off your final answer at the end, not in between. So if I look at the learning check here, let's see real quick. I hope you will use your calculator in A. I'm just going to give you real quick the answers for A. Here, you'll have 17 point, you should see A 17.00 because of what? Because of the 2 places of decimal. This has 3 places of decimal. And then B, because of division, 3 significant. If I look at this has 3 significance. The zeros do not count 3 significant, and should be 0 point what? 0.869. Please check that. Those are the answers for the learning check. Answers for the learning check. All right. Let's look at the lastly the dimensional analysis or factor label method. Factor label method or dimensional analysis is a powerful method of converting units from one system to the other one, all right? Or converting unit from one unit to the other unit, or if you have unit 2 to unit 1 using what we call conversion factor, you are doing the what? Dimensional analysis. If I ask you to convert 1 hour to seconds, you'll have to use dimensional analysis to arrive at the answer, unless maybe, of course, you know offhand the answer. But if I ask you, convert 1 year into seconds, 1 year into seconds, and then of course you have to go down sequentially until you end up with the required unit using dimensional analysis. I know everybody knows how to use dimensional analysis, all right, in changing. Here is equivalent statement, which is used to derive what we call conversion factor. Conversion factor is what you are using to change from this unit to this unit. So here is unit 1, all right? You multiply by conversion what? Conversion factor to give you unit what? Unit 2. This one you have to derive. For example, 2 conversion factors from that is 1 inch over 2 what? 2.54 centimeters, or depending on what you're looking for, 2.54 centimeters over 1 inch, over 1 inch. These are what we call conversion factors. All right. So you can derive from key equivalent statement to conversion factors. It's a just comparison. If you look here, this is for changing centimeters to inches, and this one is for changing inches to what? To centimeters. What this means is if you're looking for, let's say 98.0 degrees, not degrees, but inches, all right? Look at these inches. If I want to change inches, for example, here, I'll multiply by inches here, and then centimeter. So this is going to be 1, all right, inches and inches, and this will give you inches 38.6 inches. This is what you should see, all right. When you use dimensional analysis, you'll convert that. If it was the other way around, of course, you'll have to set up your equation appropriately so that you reconcile the units. So given, use a conversion factor and see what you are looking for. Let's see here. An example here, perform the following conversion, 5 days to seconds. So if I'm doing 5 days, and remember, we have what? We have 3 significant digits. So final answer should have 3. Why not 5.0? Why 5.00? Meaning we need to use the correct number of significant figures. So 1 day, all right, you can move from days to hours, all right, 24 hours, and then times. Of course, everybody knows this, 1 hour, 3600 seconds. If you look at the unit reconciliation, I'm left with seconds, and this will be 432,000 seconds. Zeros are not place of decimal, so they don't count. 432 significant figures, 3 significant figures. That's the answer. Unless you express in scientific notation, it's up to you. So this is A, and B, using dimensional analysis, mouse to, you want to change mouse to meters. What I'll recommend and I will share is some of the common equivalent statement. I'll send it to you so that you can have it before you learn out of those equivalent statements. For example, at the back cover of the text, you may see some. For example, 1 mile, all right? 1 mile equals to 1609.34 meters. Some you may want to find out. Maybe I'll give you an exam if need be, but for homework assignment, please look on the appropriate equivalent statement. So this is what we know. So if we have now 0.0550 miles, if I look at these has what? 1, 2, 3, 3 significant figures times. I want to get rid of miles. So then miles and miles will go away. 3 significant. So this is going to be 8, 8. All right. This is not a place of decimal. It's going to be 8, 8. All right. 88.513. This is meters. We have more than what we need. All right. If I count these 2 zeros do not count. 1, 2, 3. So 3 significant figures I'm gonna count from here. I'm gonna stop here. These are non-significant, and the correct answer is 88.5 meters. 88 meters. Please get used to expressing the final answer with the correct number of significant figures. And that marks the end of chapter 1. I will post chapter 2 again. Please go on MyLab and Mastering and get started with the homework. Please attend the SI session for help. Please get started right away. You don't want things to pile up and create a bottleneck at the end of the semester. Other than that, have a good day. Thank you.